Cal, I have finished that square thing. Okay, square.
Thank you. I really appreciate it.
Let me pull this thing. Okay, do you see the screen?
Yes.
Okay. All right, so in the last class, we talked about magnetic field at the center of a flat circular coil. And that equation is B is equal to mu naught Ni. The mu naught is 4 pi times 10 power minus 7, right? So we did that. Where N stands for the number of turns and I stands for the current passing through, and 2R is the radius. And then we did the solenoid. B along the axis of a solenoid is mu naught Ni, where lowercase n stands for number of turns per meter of the solenoid. How many turns are there for every meter of the length of the solenoid? That's what that means. And then we also did this one. Those are three important equations. So that is the magnetic field strength near a straight, infinitely long straight wire carrying current, and the equation is mu naught I over 2 pi A. A stands for the perpendicular distance. A is the perpendicular distance from the wire. And mu naught, as I said again, is 4 pi 10 power minus 7. And then we'll keep going. All right, so far so good. All right, now what is for today is about when a wire carries a current and it is placed in a magnetic field, then it will experience a force. Okay, so let's find out how the force is experienced. That's what I'm going to teach you right now. So here is a wire, and the wire carries a current into the paper. So force on current carrying wire or conductor placed in a magnetic field. Okay, so force on a current carrying wire placed in a magnetic field. That's what I'm discussing right now. So if a current is going into the paper like this, right into the paper, which way is the magnetic field around it? Can you tell me that one? Which way is the magnetic field around this wire? Which way? How do you decide?
It's clockwise.
How did you decide?
Right-hand thumb rule.
The right-hand grip rule. Okay? So the right-hand grip rule, put the thumb into the paper, and you can see which way your fingers are curling, and that means the magnetic field is this way. That's a magnetic field of this around this wire, right? Can you understand this part? Okay. Now suppose you put a magnet like this, north, south. Suppose you put a huge magnet like that. Then what will be the magnetic field without the wire? Forget about the wire for the time being. Without the wire, which way will the magnetic fields be from between the two magnets? Which way? Right. So it'll be all straight like this, right? So it'll be kind of uniform wire. So you can expect, suppose the wire is not there. Suppose the wire is not there, the magnetic field will be like this. If the wire is not there, that's what you can expect. uniform magnetic field. Okay? Is that clear? Now, because the wire is sitting inside, these two magnetic fields will try to interfere with each other. These two magnetic fields will try to interfere with each other because now you're having two magnetic fields in the same place. So what will be the shape of the actual magnetic field? I'm drawing it now. You can see that's a magnetic field string. Okay, that's fine. That's fine. This is fine. And that's fine. But when it comes closer to this, can you see this? This wire, the magnetic field from the wire is to the left, and this one is to the right. So they kind of go against each other, creating a voided area. Is that clear? So what happens to the magnetic field is that it'll go like this. It'll coil around it like this. So the magnetic fields will be like going around it like this. That's what will happen. Because magnetic fields will never intersect each other. Never. Same as electric fields. They will never intersect each other. So intersection of magnetic fields or electric fields is impossible. You know why? Because if it is intersecting, that means the magnetic field can come like this and go that way. That's not possible. There's no intersection possible. So you see that none of the magnetic field lines will touch. None. But can you see there's an excessive crowding on the top of the wire? And at the bottom, it's more clear or free. So what will happen is the magnetic field is pretty strong on the top of the wire, getting crowded. And magnetic fields will never like the presence of each other. The magnetic fields will always try to push away from each other. That's why they don't intersect. So what will happen is that wire will experience a force. Which way do you think it is going to experience a force? The wire, which is sitting in the middle, it'll experience a force because there's excessive crowding of magnetic fields on the top, and there's hardly any magnetic field at the bottom of the wire. So which way do you think the wire will experience a force? Downward, because it's getting crowded. Imagine like you're sitting like this. It's relatively free here, and people are crowding on this side. So which way are you going to get pushed? You're going to get pushed this way, away from the crowd, right? So this wire will experience a force in the downward direction. It will experience a force in the downward direction. So this is what I wrote here. Force on a current carrying wire or conductor placed in a magnetic field. So which way it experiences a force is downward. All right. Now, which way is a magnetic field? Can you show which way is the magnetic field? Which way is the magnetic field here? Of the magnet. Which way is the magnetic field? Like you can tell me if it is to the east or north or south or like that. You know, you can talk in terms of
that. The magnetic field
of the magnet is what? Which way?
North, right?
You're drawn. I mean, like it is to the right, right? Magnetic field that is imposed, like the magnetic field created by the magnet. I'm talking about the magnet. Which way? To the. Which way is the current in the wire? Which way is the current in the wire?
Just going away from us.
Yeah.
It's going out, like, tell me, down into the paper, right?
Yeah.
The wire, the current is going into the paper. Which way is the magnetic field again?
Going to the right.
Magnetic field is going to the right.
Yeah, it's like intersecting it, kind of, you know?
Yeah, current is going in. Which way is the force?
Down.
Downward. So if you're looking at this as the paper, magnetic field is going that way, current is going in, and the force is downward, right? So it's not going to be practical if you're going to draw this kind of diagram in order to find out which way the force is acting. It's not practical. Just think of, like you're going to draw all these lines to figure out exactly which way the force is going to be. That's why we have the Fleming's left-hand rule. Fleming's left-hand rule. Now, can you all pick up your hands? Left hand. Okay, keep all 3 fingers at right angles to each other. Left hand, keep it like this, Jacob. I know that's your left hand, but keep it like no. Like point at somebody, and then pick up your thumb and pick out, open your thumb and the middle finger. So we have all 3 fingers are at right angles to each other, right? Now, thumb is the most important finger in your hands, right? Yes or no? Thumb is the most important, yeah? So thumb is it's like the father in the family. Thumb is like the father in the family, very important person. This finger, the pointing finger, is like mother. She gives you all the directions. Don't do this. Go this way. Go that way. And you are the middle finger. Okay, don't take any other nonsense sense. Okay, so you are this one. I'll give some symbols for it. I'll put F. Can you write F on your thumb right now? Can you write with a pen or something F on your thumb? Just like this. Just write F on your thumb. Like that. I don't know if you can see. Yeah, F, good. And then on your forefinger, write B. B. B for magnetic field. And on the middle finger, put I. That's what these fingers stand for. FBI. Okay? FBI. Or force, magnetic field, and I. Like father, mother, and I. FMI, Try to remember any way you want. FBI is easy. FBI. That's it. So what you have to do is this. Which way is the magnetic field? Which way is the magnetic field? That way, right?
To the right.
So keep your forefinger first, pointing in that direction. And now which way is the current?
Down towards the paper.
So I have to flip it. So I just keep this in the same place, and I just turn my hands to make the middle finger go into the paper. Now, which way is the thumb?
Pointing down.
And that is exactly the direction of the force. You get it? Do you understand how the Fleming's left-hand rule is actually applied? Easy. It's so easy. FBI. Think of FBI, and you can almost think of writing it down. FBI, and F is the father or the force. B is the mother, magnetic field, giving all the directions, and I is the middle. Okay, so
I'm not following on that one. How are you flipping your hand and getting the thumb to go down if you're shooting, like if you have like your?
It's like this. Keep your forefinger in the direction of the magnetic field.
Yeah.
And then hold it. Don't move its position. And now you're going to turn it about that axis. Like you spin your hand about the axis of the magnetic field until the other finger matches. In other words, you have to match two fingers, then the third finger will be the correct finger direction. You have to match two of them, and the third one is fine. I'm going to give you some examples, then you'll tell me that. Okay, suppose a magnetic field is downward. If the magnetic field is that way, and if the current is this way, which way is the force?
Into the paper.
Into the paper. Have you got that? Did you get it, Bryce? Did you get it?
Yeah, I got it.
Okay, so what you do is first you put any finger you can put. Any finger. Like I gave you two things, right? B and I. You can put I first and then make the B in that direction. So the force is going to be into the paper. So force. Clear? Mind, remember you're going to pick up the left hand only. All right. Here's another example. The current is going this way, and the magnetic field is into the paper. Which way is the force? Current is going up, magnetic field is into the paper. Which way?
To the left.
Magnetic field is into the paper, current is up, so it's to the left. That's right. Any confusions about it? Fleming's left-hand rule.
Could you do the first one again? How your B is down, I is to the right?
B is down, so put your forefinger towards you, downward, like on the paper, like down. Oh, no, don't flip your fingers. Don't flip your fingers. Always they should be at right angles like this. They're fixed. You cannot bend them. So just keep it like that, and then you can turn your paper. Turn the paper. Turn the paper that you've drawn in such a way the magnetic field is going in that direction. And then keeping the magnetic field in the same place, make the current the other way.
If we didn't have hands, this concept would be really hard to understand.
Well, if you didn't have hands, then we'll have to use some other tools for that. Like a paper clip or something which you can bend and keep it like that. Once a girl was actually saying I always get confused about this and all this, and I don't feel comfortable when I'm doing a test to raise my hands and twist my hands and all the stuff. Then I told her, okay, do one thing. Then you can actually have a little thing, you can write FBI or FMI on your fingers if you're forgetting the letters. And if someone says, oh, you're cheating, what is this F and what is M and what is I? You say, oh, F stands for my father. I remember my father by looking at that finger. And M stands for my mother, and I for myself. Whatever. All you have to do is just use the Fleming's left. And now I strictly tell you not to follow any other rules. If you're following these rules, stick with it. I gave you the right-hand grip rule first. Now I'm giving you this Fleming's left-hand rule. So stick to this Fleming's left-hand rule. It's very easy once you get used to it. Now here's another example. Tell me this. The magnetic field is to the left. The current is coming out of the paper. Which way is the force? The current is coming out of the paper and the magnetic field is going to the left.
Force is down.
Force is down. Magnetic field is to your left, so put it that way. Magnetic field is to your left, that way. I don't know if I'm showing this right. Okay. Magnetic field is to your left. And then the current is upward. So put it upward. So which way is the force? That way. Okay, any questions there? On Fleming's left-hand rule, we'll get used to it. You know, we are going to discuss so many times the same thing. The Fleming's left-hand rule gives you the direction of the force when you know the other ones. Okay. And what is the right-hand grip rule? What is right-hand grip rule for?
It gives you the magnetic field around the current.
Yeah, it gives you the direction of the current or the magnetic field. So the connection between current and magnetic field around wires. Okay. So now Fleming's left-hand rule, stick to this, FBI. Stay there. Okay, FBI. That is these are the representations. F stands for the force, B stands for the magnetic field, and I stands for the current. So that way you can actually figure out everything. So I'm giving one more example. If the magnetic field is into the paper, and if the current is that way, which way is the force? Current is downward, magnetic field is?
Force goes to the right.
Force goes to the right. That's it. Magnetic field is in, current is down, force goes to the right. Any questions there? And one more. What if the magnetic field is to the right and the current is to the left? Which way is the force?
Is it down?
Check, check, check. Magnetic field is to the right and current is to the left.
Up? Maybe.
Is that possible?
Okay.
Wait.
No force. The force is present only if the angle between the other two are at 90 degrees. The angle should be 90. If they are in the same direction or in opposite directions, no force. All right. So this is a current, this is the magnetic field, and this is the current. If the angle is 90, that's when you have the force. But if the angle becomes smaller and smaller and smaller and smaller and smaller, the force also gets shrunk. So if you have a magnetic field that way, and the current is also in the same direction, no force. You get it? So the maximum force is at 90 degrees. Maximum force at 90 degrees, and then it comes down. All right, now force formula. The force on a current carrying conductor. How to investigate it, and what exactly is the force. So to investigate it, we need a conductor, and we need to be able to measure the force on the conductor. So I'm going to draw a setup. If you can draw it on the, it's fine. If you cannot draw it, it's fine also. So I need to create a magnetic field, and the magnetic field I'm creating with the solenoid. So I have a solenoid going like this. I have a solenoid and a switch and a battery. So what will happen when I turn the switch on? The solenoid will get energized, which means it'll create a magnetic field. Which way will the magnetic field be in the solenoid? Which way? No. Yeah, which
It'll
way?
go left to right, right?
Yeah, it will go left or right, depends on which way the coils are coiling, right? So let's say there is a magnetic field that can be created, and the magnetic field that is going to be created is that way, let's say. Now, I need to bring a conductor. So now the switch is turned off, okay? Now, the conductor, I need to put it inside the solenoid. So the solenoid is a huge one. The solenoid is a big one. So I need a conductor to be placed, and I also need to measure the force on the conductor. I need to measure the force on the conductor. So now, how you can measure the force on a conductor, I need a scale. But I can't put a scale inside there, which will mess up all the magnetic field. So I have what is known as a beam balance system. So here it is. I have two rails. I don't know if you can understand this. These are two rails. Can you understand two rails like this? And these two rails are going into the solenoid like that. So the solenoid is like this, and the rails are going inside right in the middle. Is that clear? Those are two rails, conducting rails. And these two rails are actually going to sit on an insulator. And on the other side of the insulator, we have similar rails, but not connected to this. We have similar rails going this way. And there's a pan connected to the other side. So can you see the beam balance sort of system? Right? There's a knife edge here, see? Knife edge. And there's another knife edge there. Can you picturize it? Like there are two knife edge supports, and it's a beam balancing right there. And now I put the conductor here. I put the conductor on the rails. Now remember, there's no magnetic field right now. There's no magnetic field. I put the conductor on the rails, and I'll bring the whole thing to balance. Right? So the beam balance is now brought to balance perfectly. Why is it balanced? Because the mass, the weight of the rod that I put on the left-hand side and the weights in the pan, they are matching up. And the two arms are exactly equal length. Okay. So how is it possible to find the weight of the rod? Find out what mass you put on the other side. That's it. Whatever mass you put on the other side is actually the mass of the rod. You get it? So anyway, right now it's balanced. Right now it is balanced. So now I'm going to turn this thing on. I turn the switch on. So when I turn the switch on, nothing is going to happen. Because yes, the magnetic field is passing through the rod, but the rod is not carrying any current yet. And so nothing's going to happen. Okay. Now I need to make a current pass through the rod. I need to make a current pass through the rod. So I'm sending a current now. I'll take a different color. So I need to pass a current through the rod. So I have a battery. And I'm going to take this current and send it through this rail. So the current is going that way. And the current goes that way. You see what I've drawn? So the current is going in. And then the current comes out from there. And I grab it back again and connect it. So the current is going like this, into the wire, into the rod, and then comes out from the other side. Can you tell me what will happen if I send a current like this? Which way will the rod experience a force? Downward, correct. Look at that. Magnetic field is to the right. Current is into. Exactly. And which way is the thumb pointing down? The thumb is pointing downward like this. So that is a force. The thumb is pointing straight down. So what will happen? Will the balance be balanced again? No. How do you bring it back to balance? Take some mass, and then drop it into the pan. And if you put mass M into the pan and you brought it back to balance, guess what is force?
Mass times whatever the gravity.
Mass times gravity, that's it. So you can actually measure the force on that rod.
How,
You can yeah.
How do you know that the current's facing in?
It's like this. It's like the rails are like this.
Yeah.
And the conductor is like that.
Oh, it's based on the red. Okay, never mind.
Yeah. It's a three-dimensional drawing, so it's a tough thing to visualize. Yeah, the rails are parallel and horizontal. And the conductor is sitting on top. You get it? So, moral of the story, can you measure the force on that current carrying conductor placed in a magnetic field? Yes. And so you can investigate. You can actually study what is that force dependent on. So you can vary the current. So force is seen to be directly proportional to the current, which means if you draw a graph of force and current, it'll be a straight line. So when there is no current in the conductor, there will be no force. When there is more and more current, there is more and more force. Force is also seen to be directly proportional to the magnetic field. Straight line. Which magnetic field are we talking about? The magnetic field of the solenoid. The magnetic field in which this conductor is placed. Okay, so that. And the force also depends on the length of the rod. The length of the rod carrying current. How can you change it? Anyone tell me? How can you change the length of the rod carrying current? Without changing anything else, how do you change the length of the rod carrying current?
Are you talking about the red conductor, or?
Yes, yes.
You could bring the two rods closer together.
Yep. The two, the railings. If your railings are closer, then the length of the current carrying conductor is small. If your railings are taken further away, that means the length of the current carrying conductor is larger. Right? So you can vary the length. That's what I'm trying to say. You can change the length. So is the current passing through the entire conductor? No, only between the two rails. Current is not going everywhere. It's only between the two rails. So you can change the length of change the separation of the track, and then change the length. So it's found that F is proportional to the length. And then the other factor, the last factor, is F is also seen to be proportional to the sine of the angle. What is this angle? Angle, by angle, we mean angle between the conductor and the railing. Theta is the angle between B and I. Theta is the angle between B and I. So if you have, how can you change the angle? Here, if these are the tracks, this is one track, this is the other track, you can put the conductor like that, which means the angle will be 90 degrees. But if you put the conductor like that, then the angle is lesser, right? So when the angle is lesser, it's seen that the force is less. When is the force maximum? When the angle is 90 degrees. F is maximum when theta is 90 degrees. That's why I said the angle between this finger and this finger should be 90 degrees for the force to be maximum. If the angle is 0, no force. Okay. Now putting everything together, I can write the equation as F is proportional to magnetic field, current, length. How do you change the magnetic field? You can change the magnetic field by changing the current in the solenoid. You can change the magnetic field by changing the current in the solenoid, like make more current in the solenoid, that magnetic field can be changed. So putting everything together, this is your equation. F is proportional to BIL sine theta. And F is equal to KBIL sine theta, where K is a constant of proportionality. K is a constant of proportionality. K takes a value of 1 through the definition of the Tesla. Not the car. Tesla is a unit of magnetic field. Tesla is a unit of magnetic flux density, or Tesla is a unit of magnetic field. So now K takes a value of 1 through the definition of the Tesla. So what is this definition of Tesla? Here it is. The magnetic field is defined as 1 Tesla. Symbol for Tesla is T. The magnetic field is defined as 1 Tesla when a conductor of length of length 1 meter placed perpendicular to the magnetic field carrying a current of 1 ampere experiences a force of 1 Newton. The magnetic field is defined as 1 Tesla when a conductor of length 1 meter placed perpendicular to the magnetic field carrying a current of 1 ampere experiences a force of 1 Newton. So look at that equation. F is equal to K B I L sine theta. What are they saying? They're saying the magnetic field is 1 Tesla when 1 ampere current is flowing through the wire conductor and the conductor is 1 meter long and the conductor is placed perpendicular to the magnetic field, which means what is sine theta?
1.
1. Sine 90 is 1. And what is the force? 1. So what is K then?
It's got to be 1.
Yep. So that is why I said K takes a value of 1 through the definition of the Tesla. So here's the definition of Tesla in red. The magnetic field is defined as 1 Tesla when a conductor of length 1 meter carrying current of 1 ampere placed perpendicular to the magnetic field experiences a force of 1 Newton. So from now on, you're not looking at that equation as F is equal to KBIL. So your equation is F is equal to BIL sine theta. And in most problems, angle is expected to be 90 degrees. So in that case, F is equal to BIL. If the angle is 90 degree, then you just have to use BIL. You get it?
So when would K not have a value of 1?
K is equal to 1. That is through the definition. If B is not measured in Tesla, if you're measuring B in other units, then K is not 1. You know, last year we did this, F is equal to KMA, where K takes a value of 1 through the definition of the Newton. We define the force as 1 Newton. Remember that? We define the force as 1 Newton when a mass of 1 kilogram experiences an acceleration of 1 meter per second square.
Yeah, but I don't remember talking about K. But
yeah, in the honors class, I never mentioned that.
Okay. But yeah, so it only
because
changes
honors class, I don't want to trouble everybody, so I just say, all right, Newton's second law, F is equal to ma, finished.
All right,
No
cool.
problem.
So, but K basically equals 1, right?
Yeah, K is equal to 1 by the definition of the Tesla. And so this is something that is important. The next one is force on a charge. Force on a charge. So let's go back again. Here is a conductor. That's a conductor which is placed in a magnetic field. So if the current is going this way, if the current is going to the right, which way are the electrons moving?
To the left.
Electrons are moving to the left. What do you call that speed?
Drift velocity.
Drift velocity, correct. So the electrons are drifting with a velocity v. And by any chance, do you have the equation for the drift velocity? So the charge of each electron is E, and there are n electrons. The area of this conductor is A. The length of the conductor is L.
Velocity equals I over NAE.
or I is equal to NAEV, correct?
And N is a constant?
N is the number of free electrons per unit volume.
Ah,
N is the number of free electrons per unit volume. So how will you connect N with capital N? So I is equal to N over volume. Is that right? Is that right? Everyone? Yep. And then we have AEV. AL is the volume of the conductor. So N, total number of electrons, is capital N. So that is the current. And you can knock off the area. Now, using Fleming's left-hand rule, tell me, if the magnetic field is into the paper, which way is it going to experience a force? Conductor. Which way is the experience force? Magnetic field is in, current is to the left. So which way the force?
Up.
Up. The force is upward. And what is the equation for the force? F is equal to? Just now we saw that. F is equal to BIL. So the force experienced is BIL. Now let's substitute this I here. So force is B times N over L E V and then L. I substituted for current. I substituted for this. So I got that. And then times L. What happens now?
L's cancel out.
L's cancel out.
I was just about to say that, but I was muted.
No problem. Absolutely. B N E V. This is the force on the whole conductor, right? This is a force on whole conductor having N electrons. So this is the force on N electrons. So what is the force on one electron? What is the force on each electron? If BNeV is a force on N electrons, what is the force on each electron?
Divided by E.
Divided by N.
Oh, N, sorry.
Yeah. N electrons combined gives a force of BNeV. So the force on each electron is BNeV divided by so BeV. That's a force on the electron, BeV. In general, force on any charge Q is BQB. Or F is equal to BQB sine theta, if it is not at 90 degrees. So that's an important formula. Force on a charge. Force on a charge. So if a charge is running in a magnetic field, it will experience a force. Simple. How do you calculate the force? PQV. V stands for the magnetic field in which it is running. Q stands for the charge that is actually experiencing the force. And V stands for how fast it is going. So the force depends on three factors. One, strength of the magnetic field. Second, the strength of the charge itself. And speed. So will a stationary charge experience a force in a magnetic field?
No.
No. In an electric field, it will experience a force. A stationary charge can experience a force in an electric field, but a stationary charge will not experience a force in a magnetic field. It has to be moving in order to experience a force. Now, how do you find out which direction the force is? Fleming's left-hand rule. But you got to be careful. Here's an example. Suppose you have a current. Suppose you have electrons running that way. Electron is going that way. And the magnetic field is into the paper. If the electrons are going that way and the magnetic field is into the paper, which way will the electrons experience the force? So what you got to do is this. You're going to use Fleming's left-hand rule, but what is the middle finger standing for?
Current, so it's in the opposite direction.
Yes. So what you have to do is look at the charge. The charge is a negative charge. So if the negative charge is going upward, current is downward. Like down to the bottom of the page. And which way is the magnetic field? Into. So which way is the force experienced?
To the right.
To the right. So to find the force experienced by a charge, this is exactly what you do. Fleming's left-hand rule all the time. But remember, it's current I. Here's another example. This is a proton. A proton is moving that way. And the magnetic field is that way. The proton is going to the right and the magnetic field is upward. Which way is it going to experience a force? Proton is going that way. So since protons are positively charged,
Force comes out of the paper towards us.
yes, it goes out of the paper. Is that clear? Because protons are positive, the direction of the protons is the correct direction of the current. So the current is that way. And then the magnetic field is up about to the top of the paper, so the force is coming out. So force comes out of the paper. Is that clear? Did you understand force on a charge in a magnetic field? One last thing before you go. So exactly what happens to this? Okay, so if I have a magnetic field, which is, I'm going back to this electron here in this picture. So if I have a magnetic field, everywhere like this. And if I shoot an electron, into this area like this. If I shoot an electron into that area like that, what will happen to the electron? Which way is it going to experience a force?
To the right.
To the right. So what will happen? It will deflect from going straight up to going this way. But if it is going that way, which way is the force? Magnetic field is still down. So which way is the force?
Oh, it changes, so then it like curves.
It changes. See, every time it moves, it is changing. So ultimately, what do you think is going to happen?
Goes in a circle.
Perfect. It goes in a circle, keeps coiling like that. And this force that is acting this way provides the centripetal force for it to keep going round and round. So the magnetic force will provide the centripetal force for it to go round and round. Do you have in the remotest possibility know what centripetal force equation is?
I don't remember. I have my old physics book. I could go find it.
All right. So let me write it down. So the magnetic force is equal to centripetal force. So magnetic force is BQV. And centripetal force is mv square over r. You remember it now? That is the centripetal force. So if you cancel one of the v's, you see that BQR is equal to mv. So R is equal to mv over BQ. So the radius of the turn the electron is going to take is given by that equation. What is m standing for? Mass of the charged particle, in this case, maybe electron. V stands for how fast it is moving. B stands for the magnetic field strength, and Q stands for the charge. So that's an important equation. Radius of the turn taken by a charge in a magnetic field is given by mv over bq. All right, with this, I will stop. I know it's a lot, but go back again, try to comprehend the whole thing, and then, you know, it's not difficult. It's just like you got to put everything together. It's not difficult. So basically, what equations have you seen today? I know there's plenty, but what equation have you seen today? You saw, oh my God, there's a lot. Okay, so we did Fleming's left-hand rule, and then we did, we proved the equation, and we saw that F is equal to BIL, and we now saw F is BQV, and then we saw this equation, R is equal to MV over BQ. That's important equations, all important equations. All right. Stopping right now. Have a good week and have a good game. What is this game tonight? I mean, like, what is this? I don't understand. What is it? Esports. What is that? Highland something?
They're playing Rocket League, Trinity versus Highlands or something.
What is it? Is it a real game or a virtual game?
Rocket League. I know.
It's a video game.
Oh, it's a video game.
It's soccer, but you play it with cars.
Huh. Okay. I don't know. That's why I thought where from 4 p.m. it actually changed to 9:30 p.m. I said, what? Who's playing at 9:30? You know, okay. Now
Have a good weekend.
All right. See you. Take care. Bye-bye. Don't forget to finish the assignment tomorrow.
So mastering test, are we having that this year or not?
I don't know. We'll decide.
Oh,
We'll decide about 2021 soon.
When is mastering due?
Mastering is due tomorrow night, the first homework. The next homework, I think, is due next Tuesday. And the test, I'll decide what to do.
Okay. Have a good weekend.
All right. All right. Bye-bye.